So like I said, we're talking about intro to nitrogen removal today. Um, oh, looks like someone's, oh, it's Jonathan. So we're talking about intro to nitrogen removal today. Um, so, you know, to like start this all off, why do we care about nutrients? Um, so just from a, global big picture perspective, we're concerned about nutrients because, disruptions to nutrient cycles of key elements like nitrogen, phosphorus, specifically nitrogen, what we're talking about today, um, have like pretty big impacts to us. So nitrogen follows, a basic continuous pathway, and is critical to all living organisms. And so wastewater treatment plants, play a critical role in reintroducing nitrogen back into the cycle with limited environmental impact. Um, so we're thinking about, why we're concerned about nutrients. It's really this global perspective of um, thinking about the balance of nitrogen in the system. And then, like I said, for today, we're going to be focusing on nitrogen management. Um, so high levels of nitrogen entering natural waterways like rivers, the Gulf, and whatnot can result in toxic conditions, which impact animals, wildlife, um, result in depletion of DO in natural waterways, which can cause fish kills, eutrophication, excess algae growth. Um, so, when you're looking at the picture on the screen here, this pretty much what you're seeing here is the cause of nutrient pollution into the Gulf of Mexico. Um, so,
Hold on, Gulf of America.
uh, as I say, yeah, Gulf of America. Yeah, it's gonna be hard to like, change your thoughts from like something that you're so used to for so long. It's pretty funny. But, into the Gulf there was nutrient pollution, and that can cause major algal blooms. So this has a major impact on human health, wildlife, and as well as economic impacts, so like fishery and whatnot. Um, so because of these impacts, nitrogen management is important to the work we do in wastewater treatment. So just from like a big picture perspective, this is like why we care about nutrients. Some areas might not care as much because they might not, um, their wastewater might not discharge might not end up in impacted streams. But this is, like for us in Texas, this is, why we have concerns. Um, and then nitrogen enters wastewater through various pathways. So most of the sources of nitrogen are going to come from domestic sources, like wastewater from, you and me. And then other sources also include food processing waste, chemical or industrial discharges. So we have multiple ways of nitrogen getting introduced into wastewater and ending up at our treatment plants. So we're going to start off with, what are the forms of nitrogen that we're going to see? So today, um, we'll talk about, nitrite, nitrate, ammonium, and organic nitrogen. So these are the typical forms you'll see. Um, and, ammonium, that's coming from, urea or urine, which is coming from us. Um, Nitrate and nitrite, those are coming from, the biological processes that occur at wastewater treatment plants typically. And then organic nitrogen, um, that's, just a form of like a small portion of the cell mass of organisms, um, that we refer to as organic nitrogen. So these are typically like the four forms that you'll see. And then we have a couple of different ways of measuring these. So we're going to go over those real quick. So what is, I'm going to ask the larger group here, what is TKN or total kilodale nitrogen? So if I were to, look at these 4 different components, which of these components, when I'm measuring TKN, what am I getting out of that test? Or what are we looking at?
Is it a sum of all of them?
No, not the sum of all of them.
The organic nitrogen.
Organic nitrogen is one of them. And there's one more.
Ammonia nitrogen.
Yes. Yeah. So ammonium and organic nitrogen will comprise our TKN. And then we also, another measurement we could look at would be total inorganic nitrogen. So out of these components, when I'm looking at total inorganic nitrogen, what might I be looking at?
Ammonia?
That's one of them.
Nitrite?
Yep. And one more.
Nitrate?
Yep. Yeah, so all the inorganic portions. So basically you could look at your total nitrogen here and then subtract out your organic, or sum up your nitrate, nitrite, and ammonium, and that'll get you your total inorganic nitrogen. And then total nitrogen, this one's, as it sounds, it's just the sum of, all these components. So this might be important for, so none of the TRA facilities have a total nitrogen limit, but there are facilities out there in the US that do. So this, could be a consideration of you need to, in your effluent, bring all of these numbers down. So do I have any questions so far?
Makes sense to me so far.
So, something I feel like we're sometimes a little lazy about in our industry, we kind of use ammonia and ammonium interchangeably. And so I'm going to get into the nuances a little bit of why and like break down the chemistry on what's happening in the wastewater. But, sometimes you hear ammonia, sometimes you hear ammonium, and folks just kind of use them back and forth. And so, why is that? So almost all the nitrogen, organic nitrogen that's sent down the drain, or our urine, is hydrolyzed into ammonia or broken down. Hydrolyzed into ammonia, or when I say hydrolyzed, what I mean is it's broken down in a chemical reaction with water. And so in water, gaseous ammonia, NH3, is almost entirely converted to ionized ammonia or ammonium. So this ionized for NH4. And then this ammonium, what we're going to talk about is broken down later on through biological processes. But basically there's like an equilibrium balance that's happening between ammonium and ammonia. And it's really dependent on pH of the wastewater. So when we're looking at, more acidic solutions, so closer to like a pH of 6, we're favoring the ionic form, ammonium. And then when we're looking at more basic solutions, we're favoring the gaseous form ammonia. And then wastewater, however, typically ranges from, about 6 to 9. So typically what we're actually seeing in our wastewater is, ammonium. In the ionic form. However, the reason why, the reason why we kind of get a little lazy about it is this ammonia testing accounts for both forms. So we don't need to worry about this necessarily, but just like for your benefit, we're actually, seeing most of it in this form. And when you get to the higher pHs, you might see a gradient shift of that equilibrium balance, but that's kind of why you see it referred to interchangeably. So does that make sense?
Yep.
Cool. And then we're going to get into the next part, which is, how is nitrogen removed? So conventional nitrification, this is a critical microbial process that happens during biological treatment where we're taking pretty much like the oxidation of ammonium to nitrite, and we're taking nitrite to nitrate in a two-step process. And then this is carried out by, two groups of bacteria. We have our AOB and then our NOB. AOBs are handling this first step of ammonium to nitrite. And they're our slowest growers. And then the NOB are responsible for the second step from nitrite to nitrate. Our AOBs are basically taking ammonium plus oxygen and converting that to nitrite with also like byproducts of acid, water, and energy. And then the NOBs are taking nitrite and oxygen, which is getting converted to nitrate and energy. So whenever you hear about nitrification being like an acidic process, there is a step in here that has, some acid that's released. And then typically for full nitrification, when we're observing or what we consider full nitrification, we're observing ammonium at, less than 2 milligrams per liter and nitrite less than 0.5 milligrams per liter. For cruise, this could be a little different just because of the way y'all operate with your target effluent ammonium. So like it getting closer to that number doesn't necessarily mean you guys have lost nitrification. So we'll get into a little bit more about that later, but typically full nitrification for a conventional DO system is, ammonium at less than 2 milligrams per liter and nitrite less than 0.5. And then conventional denitrification is a biological step where nitrate is being converted all the way down to nitrogen gas using a carbon source in anoxic conditions, so no air. So we have oxygen for nitrification and no oxygen for denitrification. And then the lack of oxygen allows the denitrifying bacteria to pretty much utilize the nitrate as their electron acceptor and then releasing nitrogen gas as their byproduct. Have any questions so far?
No.
I did.
Okay, so we'll get into some critical considerations for nitrifiers. So we talked a little bit about some of this last time, kind of repeat it here and like build it back into like talking about nitrifiers. So back in November or session 2, we discussed, SRT and which bacteria drive our SRT selection. So we were discussing, treatment goals at each facility. All TRA facilities are removing BOD. All TRA facilities are removing nitrogen, or specifically ammonium. And then Denton Creek is the only one with a phosphorus limit. And then I believe Mountain Creek is getting one in the next couple, I think in the final phase of their permit soon. So
TD, they'll get it.
Pardon?
On the 9 NTD is when their phosphorus limit comes into play.
Oh, good. Okay. Yeah, that's what I thought. So thank you. So right now, pretty much, so we have to think about, for the most part, our heterotrophic organisms and our nitrifiers, and creating like the growth conditions for those. And then, Denton Creek has to think about PAOs. Cruise does this already, even though y'all don't have a phosphorus limit. You guys do create the conditions for phosphorus removal. But you're not having to like steadily maintain it. Because you don't have that phosphorus limit. And so we talked about, last time that our nitrifiers were the slowest growers. So they're the ones that drive our SRT. So they require, a doubling time of 1 to 2 days typically. And so that's a consideration we have to take into account with our nitrifiers is making sure we have an adequate SRT to let them grow and do what they need to do. And then some other considerations. So, nitrifiers, pH is a consideration for nitrifiers. Typically, they function most comfortably in wastewaters of a pH of 6.8 to 7.5. So that's one consideration. Another consideration that's important for nitrifiers to give them the right conditions to grow is that we know that they're going to need oxygen. So they'll be in our, we're using our aerobic zones to create those conditions for our nitrifiers to grow. And then a lack of adequate aeration that can result in completely inactive nitrifiers. So most utilities will see aeration above, 2 milligrams per liter or higher of DO. And then while over aerating doesn't necessarily hurt our bacteria, it can give us not as much bang for our buck when we get past a certain limit. So we'll talk about that a little bit later. Coming up here in a bit, but pretty much like optimizing our aeration can be a key consideration for energy savings and therefore cost savings. And then another consideration is temperature. So, in Texas, I guess we really don't have to worry about it as much. Although, I guess, Carl, I don't know how close you guys get to, I guess, trimming your SRT, but the rest of the other TRA facilities have, higher safety factors, just for the nature of what they're having to do. So you're typically not seeing much of a difference between winter and summer. Whereas, if you're at a plant up north, in colder conditions, they could be up here in this range. And so, when we're more colder, our nitrifiers don't, it's almost like we don't work as well in the cold. It's really hard to do what you need to do when you're really cold. Same thing with the bacteria. Their reactions and doubling happens slower, and so but when we're in like hotter conditions, it happens a lot quicker. So but like up north, you might see they actually might have like a summer versus winter SRT condition. So kind of when they start getting into those colder months, they might actually start moving into higher SRTs to make sure that they're maintaining their minimum plus their safety factor. But then like in Texas, we really don't see that much of a change. So you won't really see like a pretty much a difference between summer and winter. So pretty much when we're like thinking about our nitrifiers, we have to consider things like, our SRT, our temperature, pH, and then aeration are like considerations we need to be concerned about. Whereas temperature and uh, temperature and SRT kind of go hand in hand, but yeah, those are some considerations we need to think about. Do I have any questions so far?
No, everything good.
Now, real quick too. Yeah, we ride that line very, very close for sake of flow and regardless of temperature or even to an extent, it's just more related to the rainfall and I issue we have. But yeah, we it's very close on the daily.
Yeah, I didn't know how close y'all consistently got to that. And then obviously your safety factor changes a little bit once you get into the winter months. But yeah, got to do what you got to do. Oh. So we're going to get into a little bit of low energy B&R and talk about, savings potentials and performance. So, why are we concerned with oxygen concentrations in wastewater? So, as we've discussed, nitrification requires aeration, and it's actually a, oxygen intensive process. So, just as comparison, the removal of 1 pound of BOD theoretically only requires about 1.2 pounds of oxygen. Whereas if we're looking at removing 1 pound of ammonium to nitrate, that theoretically requires about 4.6 pounds. So you can see like quite a big difference in the amount of oxygen we have to deliver theoretically to remove ammonium. So delivering DO into, wastewater, very energy intensive process, and by optimizing your aeration, that could result in, a benefit on electricity savings and cost savings to a utility. So pretty much over aerating, we'll get into a little bit more, but over aerating doesn't really do much to improve the process. Granted, some of your facilities don't really have they don't have turn down or on their blowers or things like that. It's not necessarily something that you can control, but optimizing where you can help save energy costs. And recent advancements in wastewater treatment have focused on how to capitalize on the physiological differences among nitrifying bacteria to reduce aeration energy and chemical addition, while also enhancing the effluent quality. So, for example, research over the last couple of decades have looked at, low DO nitrification, which has gained a lot of attention as a means to reduce energy and aeration demand, as well as operational costs. So, like what you're seeing at Cruise with low DO operations and making that shift, there's been a lot of research in the last, last decade or last couple of decades looking into this. Aerations can be typically up to 50% of your energy costs. So over the years, fine-tuning aeration savings has shown to provide energy savings, but you've also, when fine-tuning can create, some simultaneous nitrification and denitrification conditions, which have also shown to have other benefits such as carbon optimization, alkalinity recovery, reduced TN, and improved phosphorus removal. And so, in recent research, COMAMOX was identified as an alternative pathway, and we'll discuss this in a bit, but pretty much there's been a bacteria it's been identified that actually can do this full, it has the mechanisms to do a complete nitrification in, pretty much like a one-step process. This gets into kind of that explanation of why over aerating doesn't really give us much benefit. So, managing aeration is how we're going to control the environment for our biology. And what we're looking at here is a chart looking at Monod kinetics, which is really just a mathematical model that's describing, growth of microorganisms. And so we can see the reaction rate or growth rate you would see on the y-axis, and then your substrate on the x-axis. And so looking at this chart specifically, we're pretty much looking at how the rate relates to various DO conditions for nitrification. And what's showing here is pretty much from like 0 to 1, 1.5, 2. We're pretty much seeing a, as we're increasing that DO concentration, we're seeing a proportional or some proportional increase in the reaction rate. But when we go beyond this 2 milligrams per liter, we can see that like that increase in DO is not really giving us, we start plateauing. It's not really giving us much benefit beyond this 2 milligrams per liter. So that's kind of where the line has been drawn on where operations optimization.
Towards Michael. Okay.
Hey, Michael, you're on. Thank you. But yeah, this is pretty much why over aerating is not really going to give you much beyond just more electricity costs. Really doesn't give you much more bang for your buck. So when folks are pretty much talking about like optimization of your aeration system and kind of going to this 2 milligrams per liter, this is why they're thinking about this growth curve and looking at the Monod kinetics of this bacteria. So do we have any questions so far?
No, that's good.
Okay. So just this is going to dive a little bit deeper into the environmental factors controlling our biology and just some of the more of the research that's been done. So there was some research done on counter diffusion biofilm. So essentially, we have oxygen that's delivered through the center here in this gas permeable membrane. And then we have no aeration in the bulk liquid. So you can see your oxygen gradient here. And essentially, the researchers grew a biofilm on the outside of this membrane. And then we can see ammonium diffusing into the membrane from the bulk liquid. And then as nitrate and nitrite were produced, as counter diffusional, kind of going, you have two, like one substrate coming in, one substrate coming out. We have like, some anoxic conditions, with our, low or no DO conditions on the outside of the biofilm. They give us the ability to have also denitrification occurring. So this biofilm, they pretty much went and did some, fish stains or and looked at the micro profiles. So looking at the microbes and quantifying what species were there from various distances along the biofilm. And so we can see our like AOB, Nitrus ammona, Nitrospira population across the biofilm, and then also our NOB, the Nitrobacter Nitrospira. And so these charts were really just giving us, or I guess this research was really just giving us kind of more insight into competition with our nitrifiers and giving us more insight into their dynamics so that we could understand competition a little bit further. And then in 2015, our conventional knowledge of the two-step nitrification process, was overturned by a newly discovered process called complete ammonium oxidation, or COMAMOX. So that's where the COMAMOX comes from. So these studies reported enrichment of Nitrospira species that were capable of complete oxidation without that nitrite accumulation. And these species were characterized by a high growth yield and low growth rate. So when we're looking at this chart on the left, basically we had a pilot scale and full scale demonstration of the points representing, experimental measurements of specific rate tests at different DO concentrations from the pilot scale and the full scale. And then the line shows a best fit Monod kinetic model to the experimental data. So essentially creating like this best fit line for this specific pilot plant and full scale demonstration. So essentially this research was shown to successfully combine low DO nitrification with low DO P removal, demonstrated in the pilot scale and in full scale with a stepwise adaptation down and reducing the oxygen from a high DO BNR system to a low DO BNR process. So this was done at Cruz. I believe Aeration Basin 6 was kind of that test basin. So you guys did this kind of same demonstration yourselves. Gosh, I don't remember back when it was, but doing some testing, and then it's been implemented, since at full scale. So there's been a lot of research over the years, around COMAMOX. And this is something, that you're seeing at Cruz. So that's, low DO and low energy BNR. I think, Carl, are you guys going to do low DO, or is it you guys just have the capabilities of going to low DO in the expansion?
I mean, generally we have the capability of doing it now if we change our set points on our desired DO, rolling out the aerobics phase, but I don't recall there being any kind of conversation, whether it be now or with the expansions, if that was something that we were going to be pushing for.
Yeah, I know you guys are, because you guys are implementing like ABAC, right? Ammonia-based
Right.
airflow control. Yeah, because that would give you the controls you would need to do this. I just didn't, I guess I just didn't know the intention, if it was intended to be like low DO, or if you guys were just doing it for ammonium optimization.
They just having the capability of it, yeah, wouldn't be a bad thing, but
Do I have any more, or do I have any questions? Low DO section's kind of research heavy, but just a lot over the years that Cruz has done. That's, in line with a lot of research that it's applicable to what you guys are doing. Okay. Going to move on to, potential signs of inhibition and causes. So, what might be, we're going to kind of go over like what might be inhibiting our nitrifiers. So if we're seeing ammonium bleed through or nitrite lock, typically that means our nitrifier population isn't working. So typically because in, the effluent ammonium for like low DO systems are going to be higher than conventional already. So, that too might not be a good gut check, considering Michael at Cruise, y'all's target out of zone C is around 1. And you guys are kind of running manual right now. So I think it's higher than that. Or manual aeration because your ABAC system's not, needs some valve and actuator replacements. So that higher effluent ammonium for y'all's and maybe not indicative of your nitrifiers being inhibited. But for the rest of the TRA facilities, high ammonium or nitrite lock would mean, something's happening with our nitrifier population. And so we're going to be going over, so asking the larger group here, got just some like 4 potential questions that we should be asking. So if you're having ammonium bleed through or you're in nitrite lock, what are some things you might be looking at?
Air.
Yes. So do we have enough oxygen? So that's one of the questions.
Do you have any mechanical failures? Are you not returning quickly to where you're not finding your clarifiers?
That's a good one, Carl. I don't have that on here.
No.
SRT.
Yeah, SRT. So is your SRT set correctly? So I talked earlier also about, so I said SRT, temperature, which kind of go hand in hand, oxygen, and then there was one more I'd said earlier.
pH.
Yeah, pH disturbances. So our nitrifiers don't like pHs outside of the range of 6.8 to 7.5.
Yeah.
And then there's one more that's usually like the last thing that we go to. So what might be the last thing you're looking at? If you've done everything you can in the plant, what might be the last thing you're looking at?
Are you getting slugged with something?
Yep. Yeah. So mine get a toxic shock load. So typically we, stress like look at the conditions that you can control first. So like looking at everything in the plant and seeing what you can do to figure out if there's something you're doing to yourself before you kind of look at outside the plant. Mostly just because like if it's something outside the plant, a little harder to deal with. But yeah, and then Carl, you guys have like a procedure whenever you guys see something going on. You guys typically go and start grabbing, influent samples to kind of help catch that influent load. So those are things that like folks can do to like, in your procedures to make sure that, if you have something coming through the plant, if your primary clarifiers, probably grab it after your primary effluent, or maybe grab both influent and primary effluent, just since the if you're seeing it in your aeration basins, you probably you might miss it if you go straight to your influent. But yeah, those are some things that we can be looking at for or like asking about. And so this is kind of to help. It's kind of why we wanted to do this session before we did activated sludge troubleshooting part 2. Is kind of like help prep and then get into the troubleshooting problems next time. So, and then we're going to talk about now, what might be inhibiting our denitrifiers. So this is when, your nitrate is increasing in the effluent, and that means, our denitrifiers aren't working. So you'll probably have like a typical concentration of nitrate that you expect. And so if you're seeing that number increasing, that could indicate, look at what's happening with denitrification. And then your effluent nitrate for nitrification only plants is already going to be high because you're not having denitrification happen in your basins, because you don't have simultaneous nitrification and denitrification or anoxic zones. So Ray at 10 Mile, you guys aren't trying to denitrify in your process. So high nitrate's not necessarily something you're concerned with. So looking into some questions we might be asking. So, what should we be asking ourselves? If we're having issues with denitrification, what are some things we want to kind of like look into?
I think one thing that should be the anoxic zone. You got to make sure that we don't have a lot of oxygen or, well,
Yep.
you got mixers. Normally you got mechanical mixers, but when I was working at the Mesquite plant, we had an issue with, it was an engineer design. The flow was passing through the uh, anoxic zone, and then it was going into the oxic zone, and then for some reason the the flow was returning back to the anoxic zone from the oxic zone, and it was putting air back into the anoxic, and that was completely disabling the denitrification.
Yeah, exactly. So denitrifiers don't work in air or in an aerated zone. So you need to make sure that there's not, like, you have mixing to keep your solids in suspension, but not introducing air into it. So yeah, that's exactly right. And then what else might we be looking at? So we need air for nitrification. What do we need here? Let me see on what do our denitrifiers require to do their step? What does nitrate need?
Well, probably this is not is not one of the answers, but sometimes is making sure that the recycling pump of the we have plenty is working properly to return the nitrates into the anoxic zone, so we can do the denitrification.
Yeah, having your nitrates to be your electron acceptor. I'm looking for is, do we have enough carbon? So carbon's required to do this process. So if we don't have carbon, that could inhibit our denitrifiers and keep them from doing what they need to do. And then the last one,
Alkalinity.
yeah, looking at like alkalinity and pH, something that we can. So there's other things too. This is kind of just like some quick questions, and then we'll get more into detail and diving into some actual like troubleshooting problems on the next session. And so we're gonna. Oh, I guess, do we have any questions on that? Then we're gonna start our last section. We're gonna kind of just touch on this, just because not really applicable to everyone but crews, but I think it's something, it's something interesting. So there's other nitrogen removal pathways. So there's a lot of research, going on looking at, is there a way that we can so it's something we do in the side stream, but like a lot of research going on in the mainstream about, is there a way that we can take ammonium and get it over to nitrogen gas, either via nitrite shunt, so where we bypass nitrate altogether. And what happens is we get an oxygen demand savings of 25% because we're not doing this process. And then we get a carbon demand saving of 40% because we're not doing this process. So that's a pathway of interest that there's a lot of research going on around. And then another one is deammonification. So this one where we have 1 mole of ammonium, 1 mole of nitrite, those two come together and pretty much we get nitrogen gas. And so this one would have, oxygen savings of 25% and then 100% carbon savings. So you're not having to do this denitrification step at all. So you're basically taking your ammonium and your nitrite and immediately converting it to nitrogen gas. So pretty much whenever we're looking at like side stream treatments, PAD, I think post aerobic digestion was a process that we were looking at that kind of did this process. And then, deammonification that's going in at cruise, that side stream treatment. You're looking at this process here with Anammox bacteria. And then, why might this be hard to achieve in the mainstream? So why there's so much research going on right now? This process at normal temperatures is really hard to stop. So this NOB, this wanting to convert nitrite to nitrate is really hard to stop. So coming out of at cruise, what's happening is it's coming out of anaerobic digestion. That filtrate is hot, or hotter. It's pretty high temperature. That's why I think Eric was bothering folks for like filtrate temperature. It's for the deammonification design, just to make sure that we had the right. We didn't need to put like a heat exchanger or anything on. The temperatures in the wintertime when it got a little too cold. But basically at these elevated temperatures, we're able to allow Anammox to outcompete and actually do this conversion process. Whereas in the normal mainstream, this is a really hard process to stop, this full nitrification. So it's kind of why there's a lot of research going on around it right now. I think folks have done it, but not stably. So it doesn't, like it's been able to happen, but not, it pretty much breaks down and starts, fully nitrifying. So there's just a lot of research going on to see if this is possible, and yeah, something to be interested in and watch if you're kind of interested in that kind of stuff. But yeah. And then that's all I've got. Anyone have any questions?
Nope.
Oh, good here.
Cool. Well, go ahead and stop the recording, and yeah, thanks for joining.